In this video, we're going to continue our exploration of collections and iteration, and we're going to reinforce some of the concepts of abstraction because we see that a lot when we're thinking about collections and tasks associated with collections. We're also going to think about how we might remove items from a collection and see some of the ways in which that's either not possible or potentially error-prone. And we're going to use that as a lead-in to a future topic of the iterator abstraction. So far we've met the ArrayList class from the java.util package, and that package contains several classes that support the collection abstraction. So the abstraction that we want to group together related objects in some way. And we've seen ArrayList so far. Well, list is an abstraction for an ordered collection that may contain duplicates. And in a future video, we'll look at an abstraction that does not allow duplicates to be stored, which we call a set. In addition to the ArrayList class, there's another commonly used class from the java.util package that is called LinkedList. As its name suggests, LinkedList also supports the list abstraction. So we're going to think about the LinkedList class and compare and contrast it with the ArrayList class, because sometimes we'll want to use an ArrayList, sometimes we'll want to use a LinkedList to store a collection of objects. And it can be helpful to understand the differences in order to decide which is the most appropriate of those types to use. In terms of usage, the LinkedList class is almost identical to the ArrayList class. In any of the examples we've seen so far, if we wanted to replace the creation of an ArrayList object with the creation of a LinkedList object instead, then pretty well all the rest of our code would remain unchanged. The ArrayList class provides methods like add and get and size that we've seen used with the ArrayList, as well as a number of other methods such as clear and remove, which are also part of the list abstraction. So seemingly ArrayList and LinkedList are identical in terms of what they provide, and that's because the list abstraction hides the underlying implementation details of those two classes. But sometimes it can be useful to understand the differences between two similar classes in order to appreciate in which circumstances one might be better than another. So we're going to spend a little bit of time looking at the internal implementation details of both the ArrayList class and the LinkedList class, although we'll only do that at a relatively high level. When we create an ArrayList object, internally we get something that looks a little bit like this. At the top in red is our ArrayList object, which is defined to store a collection of some arbitrary type such as element. Internally, the ArrayList object makes use of an additional object which is called an array, which is where the ArrayList class gets its name from. And it's the array that is responsible for actually storing references to the objects that we notionally think of as being inside the ArrayList. So that array has some capacity, a capability to store some number of objects, and the objects stored within the ArrayList will be stored in consecutive locations of that internal array. However, we note that the array itself might actually have space for additional objects to be included, but those slots are not yet occupied. And that's an important feature of the way that the ArrayList class is implemented. So an ArrayList, when it's created, actually internally creates an array with some capacity, and then as we add objects to the ArrayList, those objects are added into consecutive locations in the array until that array fills up. Now the question then arises, suppose we wish to add more items to the ArrayList than the internal array is capable of storing. Well, in that case, what the ArrayList does is it creates a larger array. It copies the contents of the original array into the new larger array, and then in fact it throws the old array away because it's no longer needed, it's too small. And so the newly created array again will have a larger capacity than is needed currently for the number of items that are stored, and therefore it can receive more objects that we choose to add to the array list. And that whole process repeats as we add more and more objects to the array list. The internal array fills up, a new one's created, the contents of the existing one are copied to the new array, and the old array is thrown away. So the array list seamlessly goes on and on expanding simply by creating larger and larger internal arrays to contain the objects that we wish to store within it. So that's a look at some of the internal workings of an array list. A linked list object, although it provides the same external functionality as an array list, internally is implemented completely differently. A linked list object does not use an array to store the items that are part of the linked list. So for each item that we wish to store in the list, it creates a helper object that's responsible for storing a reference to one of our elements. And then it chains together those helper objects in what's called a doubly linked list internally, and then the linked list just keeps track of where the head of that linked chain of helper objects is and where the end of that chain is as well. And then that chain of helper objects gives rise to some of the characteristics of the way that a linked list behaves when we call various methods on it. Now, in very simplified terms, we can ask questions about how fast or how slow different operations are on those two types of lists that arise from their internal implementations. And these are broad generalizations. You can always make your own practical tests to find out just how fast or slow these various operations are for large numbers of objects. But in general, we can say that for an array list, whenever we call its get method, then the array list is able to return the reference to the object that we want very quickly. In fact, it doesn't make any difference what index we provide to the get method. It will be able to return the object we want in exactly the same time. If we wish to add or remove elements from the very end of the array list, then again the array list is able to respond to that operation relatively quickly. On the other hand, if we want to add an item or remove an item from somewhere other than at the very end of the array list, then the array list has to take a little bit more time to organize that. The reasons for that are that if, for instance, we consider adding an item at the beginning of the array list firstly has to move all the existing items down by one position in order to make space for the new item. In the case of removal, if we were to remove from the beginning of the array list, for instance, then you'll recall that we don't leave gaps on removal, and so all the items to the right of the one that's removed have to be moved down one place left in order to fill in the gap. So the addition and removal require some additional manipulation of the internal contents of the array list, which effectively slows down the operation. Moving to the linked list implementation, because the linked list only keeps track of the beginning and the end of the list, if ever we use the get method with an integer index, it actually has to locate where in the list the item is that we want. And that's a relatively slow process, as internally it moves from the beginning towards the index that we want in order to find out exactly where the item is in order to return it. So the get operation on a linked list is much slower than it would be on an array list. Add and remove at, in fact, either end, so the beginning or the end of a linked list, is relatively fast. So no internal rearrangement of objects is required in that case. The add and removal for elsewhere, the actual time it takes varies, and it varies for two reasons. The part where we wish to actually locate the point of either addition or removal is a relatively slow operation because, as noted before, if we use an index into a linked list, then the linked list actually has to laboriously find the required position. On the other hand, the actual process of removal of one of those items from the list is a relatively fast operation because all that's required is for the helper node to be removed and some rearrangement of those internal links between the nodes either side of the one that's being removed. And that's a relatively fast operation to perform. So when deciding whether to use an array list or a linked list, we can take some of those broad characteristics as aids to helping us to make the decision. Let's look at a couple of examples in practice of relatively simple operations just to put these fast, slow ideas into context. So in the first example, we are iterating over a list and we wish to process every single item in the list in some way, and we're using an integer index in order to access successive elements of the list. This iteration will be relatively fast for an array list because each time we call the get method with an integer index, the list doesn't have to do any special work in order to find out which item it is that's got to be returned. On the other hand, with a linked list, every time we call the get method, then the list has to find that particular position regardless of the fact that it was just one beyond the position that it found the previous time around the loop. And so that's a relatively slow operation. Now, considering the second example here, what we want to do is we want to remove an item from the list at a particular index and then reinsert it at the beginning of the list. So we're moving an item from wherever it is within the list to the beginning of the list. For an array list, the removal process is relatively expensive because there are two moves of the remaining items in the list. Firstly, when the item is removed, then all of those items that follow it in the array list must be moved in order to fill in the gap. And then when we reinsert it at the beginning of the list, then all of the existing items have to be moved right one place in order to make room for the new one to be added. With the same operation performed on a linked list, then again, locating the item is relatively expensive because we're using an index in order to find its position. Taking it out of the list is relatively fast because we just need a small amount of rearrangement of those links between adjacent nodes. And then reinserting at the beginning of the list again is relatively cheap because nothing needs to be moved around. It's simply a case of creating one of those helper objects and linking it in right at the head of the list. So contrasting times to do some fairly standard operations on either an array list or a linked list. So we've begun to think about the fact that having got a collection, we might want to make some manipulations of that collection. And we want to focus now on how we can safely remove items from a collection. And from the previous example, it might seem, well, it's not particularly difficult to remove an item from the collection, but actually it turns out that there are a few little wrinkles that we need to think about before we just plunge straight in and write code to remove items. There will be many situations in which the contents of a collection are not static, that we want to add items, we want to remove items, perhaps we want to move items around within the collection. And care is particularly needed when using iteration to remove items. And we're going to look at a specific example in the context of the music organizer in a few moments. Before we do that, we're just going to make a slight refinement to the way that the music organizer program works. So up to this point, we've thought about using the music organizer as storing a list of file names, where those file names are the audio tracks that we wish to play. That's not terribly flexible. It would be nice to add an abstraction into the project where we could talk about tracks, and by track we mean a piece of information that can identify who the artist is, what the title is, and what the associated file name is in which that music is stored. So from this point onwards, and in version 5 of the Music Organizer project, we're not going to be storing a list of strings anymore. We're going to be storing a list of track objects, and therefore each object stored in the collection will have an accessor method for the artist, an accessor method for the title, and an accessor method for the file name where that audio is stored. Suppose that we want to iterate over our list of tracks, and there's a particular artist that we no longer want their works in our music organizer, and so we're going to iterate through. Every time we find a track that matches the artist, then we want to remove that track from the collection. If you're used to thinking of iterating over a whole collection purely in terms of the for each loop, then you might be tempted to write code something like this. We've got a for each loop where for every track in the list we call the accessor method for the artist information, and then we make a comparison between that and the parameter value, and if the artist of the track matches the artist parameter, then we say to the tracks collection, please remove this track. And I want to illustrate that you cannot do this with a for each loop. So let's switch to the BlueJ project Music Organizer version 5, and let's take a look at what happens when we try to write our code like this. Here's our Music Organizer, and here's our method to remove all the tracks by a particular artist using the for each loop code that we've just seen. Let's see what happens when we try and run that. Create a Music Organizer object, and we can see that we have 4 tracks, the ones we've met before. Suppose that we want to remove the tracks by the artist Blind Lemon Jefferson. So I'll copy from there and call the remove by artist method, pasting in Blind Lemon Jefferson, and click on OK. Now the program has crashed, and it's crashed with an error down here, which is a concurrent modification exception. So what's happened is that as we've been iterating around the collection, we found an artist who matches, we've attempted to remove them, and at that point the program says you cannot modify a collection when you're using a for each loop. So the program crashes at that point. And this is a mistake that lots of people make. They're used to using for each loops to iterate over collections. They try and modify the collection either by removing or adding, and the program crashes with a concurrent modification exception. So this just reinforces the principle that you cannot use a for each loop if you want to modify the collection being iterated over. So we need to find an alternative to complete this process. So we get a concurrent modification exception if we try to do this. If we can't use a for each loop, then let's try using a while loop. So here's similar code where we set up an index, we iterate over the collection while the index is less than the number of tracks inside the collection. We get the next track using the index, we retrieve the artist, and if the artist matches, then we pass the index to the remove method, remove the track, and move on the iteration. Now what the title of the slide suggests is that this is logically wrong. There's an error here, and it might be worth spending a little bit of time just looking at this and trying to understand what's going to go wrong. We're not going to get a concurrent modification exception as we do with a for each loop, because it's perfectly legal to modify a collection while we're iterating over it using a while loop. The problem is actually a logical error. What that means is that this method will actually work a large proportion of the time, but there will be certain circumstances in which it will fail to work. In other words, it won't fully remove all of the matching artists from the collection. It just requires a little bit of thought as to what the circumstances are where that could arise. So let's look at that in practice. Here's our code rewritten to use a while loop, and let's see what happens. We create a music organizer. There are the tracks. Once again, we'll remove all those by blind lemon Jefferson. And let's just check to see whether they've all been removed or not. And it seems that everything's working fine. There are no tracks by blind lemon Jefferson any longer. But let's look at this one more time. Let's create a music organizer. And now let's remove by artist blind lemon Jefferson, and notice that now we still have a track by blind lemon Jefferson in the list. So what's gone wrong this time? As you can see, it's exactly the same code in the remove by artist method. However, let's take a fresh look at the tracks that were read and printed out when we first created the music organizer. And what's different in this version is that the tracks are sorted by the name of the artist. And as a result of that, all of the tracks by blind lemon Jefferson have been grouped together. Now, if you notice, the track that remains from blind lemon Jefferson is the one after the one that's been deleted. So this is the flaw in the approach that we saw on the slide. The problem is that the code does not recognize the fact that the indices change when we remove. And every time around this loop, we always go ahead and move the index on by 1. And as a result of doing that, we end up not actually checking an item that immediately follows one that has just been removed. So we have to remember that removal changes indices, and therefore this code is logically incorrect. There will be some arrangements of the items within the collection for which it fails to operate correctly. So what we actually need in order to remove items safely is something that can take into account the fact that items might move when a collection is being iterated over and having items removed. Now, all of the collection classes in the java.util package support the use of the iterator abstraction. And furthermore, as well as providing a safe means to remove from a collection, iterator also provides an efficient implementation of iteration. Now, I'm describing iterator as an abstraction because the implementation of that abstraction differs for each particular type of collection that we might want to use it with. So we've seen that linked list gives us relatively poor performance when we want to use an integer index in order to iterate through it, in contrast to an array list. But the implementation of iterator for a linked list takes that into account and is able to provide an implementation that is just as efficient over a linked list as it would be over an array list. So the iterator abstraction is very powerful when we want both safe and efficient iteration over a collection. To review what we've talked about in this video, we've seen that both ArrayList and LinkedList support the list abstraction. They have broadly the same set of methods, and we can often use them interchangeably. but their distinct implementations affect the efficiency of those different operations. And being aware of those differences can be useful depending upon how we're planning to use the collections, the sort of patterns of usage we might have of addition and removal and lookup. We've seen in action that if we want to remove items from a collection, then we cannot use a for each loop. And we should never think of using a for each loop when we want to modify the contents of a collection. We've seen that removal from a collection using integer indices can be error prone, and in some cases, such as with the linked list, it can be relatively inefficient. And in a future video, we'll see that iterator is well suited to iteration that's both efficient and safe.